I'm going to say 1.8 times 10 to the minus 5 will be equal to x times x over 0.250 minus x. These are all 1-to-1 ratios. And now I need to solve this problem. Now to solve this problem, I want to use my solver in my calculator. So if you're using a TI whatever calculator, you're going to do math and then find the solver. It's actually the 0 button. And you're going to type. Now I really believe in the cross multiplication method. So this times this is equal to, say, the black line is equal to the blue line as it's drawn on the screen. All right, but basically it has to be set equal to 0. So you can say 1.8 e negative 5 parentheses, that's going to do it times 0.25 minus x parentheses, and that's equal to x squared. Since I have to set that equal to 0, if I subtract x squared from both sides, then essentially this can just be minus x squared equals 0. So if you type your calculator, this right in here, you solve for x. Now x is going to be a really kind of tiny number. I know that already. Now how do I know that, do you think, Mr. Sams?
Well, it's a weak acid, so only a little bit of it is going to dissociate.
And because the Ka is very, very small, 10 to the minus 5 is a pretty small number, it's not going to happen very often, or very, often, maybe not the right word, but you won't have very much dissociation. So what is x equal to, Mr. Sams?
I'm putting that in my solver here, and I get 0.00211.
Now, a warning, when you do these on your solver, oftentimes you're going to get you're going to get a number that you may have to scroll over to find the times 10 to the power of something. So just watch that. This one didn't do that. But what is x equal to? We have to kind of go back to our equation.
Right.
X equals the concentration of the hydrogen, and it equals the concentration of the acetate. What was the question again? It says what is the
pH? Should we just take the negative log of our x value?
So then we just say negative log of 0.00211, and that will be
negative log of x is 2.67.
So that's the answer. Now, a shortcut, those in internet land, hopefully you're following, we primarily use TI 80-something calculators, and that's why we're walking through the solver method. But you can also just say negative log of x. Your calculator already knows what x is because it's solved for that, and it stores in it sort of its temporary memory until it gets overwritten, which we'll probably do in just a minute again. Okay, so that's that question. Second question, what is the percentage dissociation of a 0.325 molar solution of formic acid? So first of all, we have to know something about formic acid. So we go back to our cool table guy and we find formic acid. I hope we have it on here, do we?
It's not. I'll go look it up.
Okay, so we need to know the Ka of formic acid. Our table is not totally complete. Formic acid is HC. We'll figure it out. Hold on. Formic acid is HCO2H. Probably should have given that. Okay, but HCO2H then dissociates into H positive plus CO2H negative. And the Ka, what was the Ka, Mr. Sams?
1.8 times 10 to the negative 4.
Similar to the last one, but 10 to the 4th and minus 4th instead of 5th. All right, now you're going to do the same thing we just did, folks. You're going to say 0.325, 0 and 0, minus x plus x plus x. 0.325 minus x, x, and x. So I can then say 1.8 times 10 to the minus 4th. You'll see that we haven't gotten to the percent yet, but you'll see, is equal to x squared over 0.325 minus x. And when you do the whole solver thing, just as we discussed previously, you just need to figure out how to do this. And it'd be good to pause the video and make sure you get this value. You find that x is equal to what? Mr. Sams is almost there. He's solving it on the calculator right now.
It is 0.00756.
Okay, so that is x. Now, but what is x? Well, it's the concentration of the hydrogen. So if I wanted to find the pH, I could just take the negative log of x. But it didn't ask for that. It asked for the percentage dissociation, which means what percentage of the 0.325 broke up. But if you think about that, it is actually the amount that broke up was x. So to do the percent dissociation, you're going to take x divided by your initial amount, which of course will be 0.00756 divided by 0.3325 times 100, of course, for percentage. And you get a what percentage dissociation?
2.33.
So this number is 2.33. I think. Maybe we do.
Yeah, 3 sig figs.
Yeah, there's 2 sig figs up here.
Oh, yeah, you're right. Probably
so 2.3%. So breaks up 2.3%. So percent dissociation, this would be important to know. It's basically your x divided by your initial amount. It's actually times 100. So that's how you do those percentage dissociation problems. All right. Okay, I like this question. We have a solution where we have 1 molar hydrocyanic acid and 5 molar nitric acid. Nitrous acid, pardon me. Also calculate concentration of cyanide. Okay, it's quite a long problem.
Yep.
Technically, we have a weak acid, HCN, and another weak acid, HNO2. What do you think we need to do?
Well, figure out which one's stronger to start with.
You think so? Actually, I wouldn't do it that way. If they're both weak acids, I would have to do both problems and add them up.
That works too.
So I would do the HCN first. So HCN, we're going to get redundant here, I think, is going to break apart into H's and cyanides. This hydrocyanic acid was a 1 molar. That's pretty high, probably compared to most. Well, the next one is 5 molar. So 0, 0, minus X, X, and X. 1 minus X, X, and X. And then we look up the Ka value of hydrocyanic acid from the table, which was 6.2 times 10 to the minus 10th, and that will be equal to x squared over 1 minus x. So x for this one, which is equal to the concentration of the hydrogen, right, because that's x right here, is, now Mr. Sams is furiously doing
punching it into my calculator.
Solver man. He's becoming the expert solver guy. The solver guy is working very hard on the solvation, not the solvation, the solution to the problem. Mr. Calculator Math.
Ooh, I got a negative. That's not good.
Mr. Sams didn't do it right, so he's continuing to work on solving the solver problem. You make a better guess.
There we go. I got 2.49 times 10 to the negative 5.
2.5 times 10 to the minus 5 molar.
Okay.
We then have to then do a separate problem. This is tedious, I apologize, but it is what it is. The nitrous acid is going to dissociate into the hydrogens plus the nitrite. And this is a 5 molar solution. It'll be minus X, X, and X. 5 minus X, X, and X. So in the Ka of nitrous acid is 4.0 times 10 to the minus 4th will be equal to x squared over 5 minus x. When you solve for x, x is still the hydrogen concentration, and that would be equal to, Mr. Sams?
4.5 times 10 to the negative 2.
So what do we do with these two numbers now, our two different hydrogens concentrations?
Got to add them together.
We simply add them together. And I think I can do this in my head. You know what the concentration of the hydrogen? I'm going to call it 4.5 times 10 to the minus 2. How did I know that?
Well, 10 to the negative 5th numbers are way smaller than 10 to the negative 2 numbers, like 1,000 times smaller.
So if you add these two numbers, this number wins. I mean, it's just huge compared to this number. You know, it's kind of like, you know, if you are standing on the scale at home, and they're weighing you, and I say, oh, let me give you a pencil. What's going to happen to your weight?
Nothing.
It's going to go up a little bit, but the weight of the pencil is insignificant compared to the weight of Mr. Sams.
Yeah. Hey, what are you saying?
Well, you know, you need to exercise more.
I do need to exercise more. I won't argue with that.
All right. Did it ask for the pH?
I believe it does. Yeah.
So pH, of course, is just the negative log of this.
Yep. We get 1.35.
And then you get 1.35.
And that's an acidic pH, so that makes sense.
Yep. Mr. Sams is actually not fat. I was just.
But I do need to exercise.
You could exercise more.
Yeah.
Okay. How about this one? Okay.
Well, but we also asked for the concentration of the cyanide ions. In
it did. So what is the concentration of the cyanide ion?
That would be X from the first problem, it looks like.
So this right here is the concentration of the cyanide ion.
Yep.
You just, boom, right there.
Ta-da. There it is.
In blue. Okay, good.
Okay.
This next question,
page.
which is almost the last page.
Okay, this one we have a mixture of nitric and nitrous acid. Now that one, we have a mixture of a strong acid and a weak acid. And this is weak. Now, we could go back and solve these problems, but I'm going to just tell you, folks. Actually, we already have done nitrous acid, although not the same concentration. No.
You could do, basically, the nitrous acid is going to be HNO2, dissociates into H's and NO2 minus. And this will be the X, 0, X, plus X, X, 0, plus X, X, and this will be 0.25, I'm going that over, sorry, minus X, 0.25 minus X. So you're going to have to with X squared over 0.25 minus X is equal to Ka.
The K value.
Which was a pretty big one, really.
4.5 times, no, 4 times 10 to the negative 4.
4.0 times 10 to the minus 4th.
But guess what?
The other one, the problem with that is the nitric acid.
It's strong. It wins.
It wins. It's going to completely dissociate. So the concentration of the nitric acid from the nitric acid, a little tricky on this one because we are pouring 25 milliliters of each together. So the actual concentration is not 0.25. Actually,
no.
You know what? We made a mistake here. This is going to be what? 0.125.
That's going to be, yeah, half of that.
Now, how did you do that without doing that M1V1, Mr. Sims?
Well, you just doubled the volume, so you cut your concentration in half.
Yeah, folks, that's an easy thing. If you double your volume, the concentration gets cut in half. So this is just 0.125. So if you take the log of 0.125 or the negative log.
Negative log, you get 0.903.
The rule is, guys, is if you have a strong acid and a weak acid, strong acid wins. And you just ignore the weak acid.
Ignore the weak? Yep.
Because, yes, that's it.
Yeah.
Okay. All right, this one's a little bit different. We have a base. So ammonia is a base. Now to do a base, we do have a table of bases. So this is the weak base or the Kb values of various bases. Ammonia, the one we have in question on this problem, is 1.8 times 10 to the minus 5. Haven't we seen that number before, Mr.
I think so. That was the Ka of acetic acid.
So acetic acid and ammonia actually have the same Kas.
They
actually,
do.
one's a Ka and one's a Kb.
And we'll
now,
talk about something nifty about
tricky
that later.
part about this is that it's ammonia. So we have to write the reaction. The reaction is NH3 plus what?
Plus water.
Yeah, we're going to say plus HOH.
Because it's a solution.
And it makes ammonium, NH4 positive, plus hydroxide.
Hydroxides, yep.
Now this right here is a liquid, and it will not participate in the equilibrium. It's part of the reaction, but it doesn't participate in the equilibrium. So the ammonia is 0.25 molar.
Mm-hmm.
This will be 0 and 0. Notice that I'm skipping the water. So this will be minus X. Here's my ICE. So 0.25 minus X plus X, X, plus X, X. And so the Kb will be equal to the concentration of the ammonium times the concentration of the hydroxide over the concentration of the ammonia. So when I plug in my values, I can say 1.8 times 10 to the minus 5 will be equal to x squared over 0.25 minus x. We then plug that into the solver. We say x equals
0.0021.
Now that's the molarity, but what is that equal to?
That's going to be equal to our concentration of our ammonium ions and the concentration of our hydroxide ions, because those are both of the x's.
And we're trying to find what? The pH, right?
Trying to find the pH.
So in this case, you have sort of an additional state. First, I would find the pOH by taking the negative log of 0021, and you get...
You get 2.68.
And therefore, the pH would be 14 minus 2.68, or 11.32.
And that makes sense because that is a basic pH.
So you only have this sort of additional step when you have a weak base problem. Okay, and I got the 1.8, by the way. I'm sure we said this right here on this table.
Yep.
And I think we're going to do one more.
We're going to do one more with methylamine.
Now we have a different chemical. This is CH3NH2 called methylamine. Now let's kind of make sure the reactions I find are hard for students.
By the way, there's a typo on this chart here.
Oh, is there?
That should be NH3 right there, not NH2.
Oh, this is a typo? Okay, thank you.
It's a typo on your handout, too. Actually, I think it's a typo in our textbook.
Oh,
I recall.
Okay, well, yeah.
Anyhow.
We're using Zumdahl's 6th edition, by the way, if you are a internet land person. So we have this methylamine. This is the chemical, by the way, that is the methylamine, and this is his